Good day to the judges. I am Leong Kai Yuan, and today I'll be presenting my Innotech 2021 entry, which is for the isolated DC-DC converter with silicon carbide MOSFET for the electric vehicle onboard charger system. There is an increasing interest in the use of electric vehicles as a green alternative to internal combustion engine vehicles, and there is also rapid development of wide bandgap semiconductor devices which have more desirable properties and have a higher efficiency compared to silicon devices. Hence, my problem statement that is addressed by my design is to implement the wide bandgap devices into the EV onboard charger so that we will be able to increase its performance and gain the benefits of such technological developments. Here is the block diagram of the design system using a DAB topology using silicon carbide MOSFETs for lower losses and size reduction at a 2 kilowatt rating. It consists of a primary H-bridge, a transformer for the isolation, a secondary H-bridge, a gate driver circuit utilizing the single phase shift control method, and finally monitoring and measuring equipment used to measure the parameters of the circuit. It operates bidirectionally, means from grid to vehicle, the source will be taken from the PFC stage over to the battery or drivetrain, and also during discharging to the grid, it can also discharge from the battery over back to the grid to sell back for peak leveling. System implementation of the full bridge door active bridge isolated DC-DC converter is implemented using Plex, using device models provided by the manufacturers, and using implementation of a silicon carbide MOSFET and a silicon IGBT model for contrast of specifications and performance. The losses of the system is measured using the thermal domain analysis provided by Plex using the heat sinks of each device, which shows the heat flow and the losses by heat. Expanding on the working principle of the design, the sizing of the transformer inductance L is given by this formula, where it's observed that the inductance sizing is inversely proportional to the switching frequency. Hence, we can say that due to the large magnitude of the switching frequency possible by the silicon carbide MOSFET, it is heavily influenced and is able to be heavily reduced by the use of silicon carbide. This also means that the transformer sizing of the system is smaller when the silicon carbide MOSFET is implemented, hence will lead to an overall smaller footprint of the design. Comparing the performance of the design to past research, it performs better than the silicon counterpart by Pang et al. And also the silicon carbide counterpart by Taylor et al. However, it performs worse than the CLLC model by Zhou et al. However, due to not requiring a resonant tank and also requiring a smaller transformer, there is less magnetic components and it requires less space overall. There is also a decrease in complexity as the CLLC model requires frequency modulation and a complex gate drive circuit. The contribution in this project by my design is that it directly addresses the needs for the EV design to reduce circuit size and weight, as there is better thermal performance requiring a smaller heatsink and also requiring lower inductance due to being able to switch at very high frequencies. This results in a higher power density and better overall performance for EV design. From the working principles presented, there are environmental, economical, and social benefits that display sustainable development for my design. Firstly, there are less and smaller components, which allows for the less waste to be generated, and also the high efficiency of the drives provides a benefit to the environment, and less parts use also means that there is lower cost for manufacturing these parts in production. Finally, as the drive is smaller and more accessible, it allows for higher adoption of EV in the society and hence will lead to a greener society overall. In addition to the sustainable development presented, there are also uses and industrial application which is applicable to my design, such as allowing for higher power density drives for development of smaller and accessible EVs, as right now the onboard charger will take up less space, and allowing for smaller cars which have longer drive time and on operation time for use on the road. There is also an application in the motorsports and racing industry, as the smaller drives allow for weight and size reduction, which is highly important to remain competitive in the field. This concludes my presentation for Innotech 2021. Thank you very much for watching.